This is ME 760, a course from the University of Waterloo, where we are studying human health risk assessment from air toxics. This course focus is on mobile sources, but all the theory will apply for stationary sources as well. This lecture focus is uncertainties that we face when we are conducting our emissions inventory, our dispersion model, and our human health risk assessment and ecological risk assessment. The segment of the lecture focuses on uncertainties. We're going to cover uncertainties and the approach we will use to analyze when there are uncertainties, but we have some idea of the distributions of variables is the Monte Carlo approach. We will cover this and talk about limitations and how to properly conduct Monte Carlo studies. Types of uncertainties can be caused by the model itself, and we are using various models. We use models to estimate emissions to the atmosphere, and that's what we did, for example, with the model called MOVES. Those are for on-road type model to estimate mobile emissions. And then we have a second model, which is the air dispersion model, where those toxics will spread once they are released into the atmosphere. And finally, we have models to assess when this hit receptors, be it human health or ecological receptors, how they are going to impact. And we need to then have models to estimate. They all have uncertainties. Parameters that we use, they are also sources of uncertainties, because sometimes a parameter can be good for a specific situation. Case in point, we have fish and transfer of pollutants dissolved in water into the fish. Those parameters are sensitive to the water pH. So we get a very perfect parameter and the pH changes. The parameter is now with a level of uncertainty that can be small or big or can change in ways our model may not consider. Decision rules are type of uncertainty introduction. They cause uncertainty because we need to have standardized ways to do things, for example. And this standardized way will then ignore facts potentially that will affect our results. This will cause uncertainty. Standards and also regulations. And finally, we have variability. We have different people. We have people with different resistance to chemicals. Some are allergic to certain chemicals. Some can take high dose of the chemical and have no response. To not know how to take all these factors into consideration. We handle this variability by assuming or measuring and estimating distributions. So if we have Gaussian distributions of people's height, people's weight, soil values, these can be taken into account, and we can use Monte Carlo models to analyze these. For air toxics, we have uncertainties on the release, on the fate and transport, and the risk calculations. What are the uncertainties on the release? We have exit parameters, and this includes the velocity. Exhaust of cars, depending on how much you are stepping on the pedal, will be different from a factory. That stack will emit with different volumes depending on the load that we have on that factory. Temperature changes. We have cold cars are riding for short rides. The engine doesn't get hot enough, and then it causes higher emissions. Release height is also an exit parameter information. We have emissions rate. These change. They change with time and may change even second by second. We may lump these all as an average over an hour, and even then it may be just a crude approximation. We do not take into account the variations that it's having as a car progresses. Car accelerating will emit much more than a car on constant speed on a highway. So these are also variations that we may not take into account, and introduces uncertainties. The phase that chemicals come out of the exhaust. We're going to have vapors, we're going to have semi-volatile organic compounds that will exit as vapors but will condense. It will condense on top of particulates that may also be emitted from the exhaust. What we have is fate and transport uncertainties. This is our next topic. We have to take into account the meta information. We need to have the wind speed and wind direction at every square meter on our domain. We don't have that. So we are approximating. We need to calculate and estimate. We need to know the cloud cover every second and every area that is being shaded by clouds. We take an overall sky average, and that introduces uncertainty. We have geophysical information. The land use is very important because if the land is wet, it will warm up much less than if the land is dry, and that temperature will then be important on the mixing of these pollutants with cleaner air surrounding the pollutants. Topography, another area of uncertainty because the measurements that we have may include the height of the buildings. So radar from satellites go over and it gets the average of the height of that area, and the average may include rooftops. Chemical properties. There are over 100,000 chemicals. They are potentially harmful to humans and ecological receptors. And these will have dozens of properties that we need to measure. We can't measure them all. So we estimate using correlations, structure analysis relationships. And how do we compute and what are the uncertainties for risk calculations? And here goes. Individuals will have different weights. They will have different metabolism. There are people that can eat almost a ton a day and gain no weight, and some people can smell the food and gain 2 pounds. So that metabolism, we do not respond. Even diets, people do not have a complete understanding of human diet. Consumption, how much people are really eating, we just estimate averages. And even distributions must be included here. They're not really well measured for every type of consumption. Location of individual could be also related to exposure frequency. For example, we do not know if a human will be in a location that is of high exposure, how often it will be, what is the behavior of that individual moving away and coming back. So this relates location with exposure frequency. That's very hard to get a very precise number for thousands of individuals living, for example, beside major roads. And then variability is related to how weight of people, metabolism, consumptions, etc. There are natural variability on everything, and we need to take account into what is the variability, how it changes, and we approximate these using distributions. The most common one is to use the normal distribution, but there are other types of distributions that are also very important. And if you assume everything is normally distributed, we can commit serious discrepancy. This is a summary of all the types of uncertainties. This list is not exhaustive, but it's very important. Most of the uncertainties will be accounted within this list, but believe me, there are more types of uncertainties that affects when you're conducting risk assessment. If you have any questions, please email them to me.